Okay, let's talk about 10.55. We're given 5 different molecules and their formulas, and we're asked, do these molecules have polar bonds? If so, which are considered very polar, which are considered not very polar in terms of the individual bonds which are present? We're also then asked, which of these molecules will have what they term to be a molecular dipole moment or just a dipole moment? This is a permanent dipole moment, a permanent molecular dipole moment. And that terminology or vocabulary might be confusing to you, but basically what it's asking you, this molecular dipole moment business, is the molecule as a whole polar? If the molecule is polar, we say it has a permanent molecular dipole moment. It's just vocabulary, okay? So let's go through this. The first one is SCl2. The first step in assessing whether polar bonds are present or whether the molecule has a molecular dipole moment is always to write the Lewis dot structure and then figure out what the molecular geometry is and what bonds we're dealing with. In this case, we've got a central sulfur with 2 chlorines single bonded, and this is the Lewis dot structure for this particular material. The next thing we need to do is assess whether polar bonds are present. We have 2 bonds, one here and one here. Central sulfur to chlorine in both cases. We know that sulfur and chlorine have differences in electronegativity, so we would say that this bond perhaps is a little bit polar, okay? So you might say that there's a bond polarity present here, okay? But the question is then for a molecular polarity, what's the shape of this molecule, and do these arrows cancel out each other, okay? So we've got to figure out, well, what is the shape of this molecule? Now I've drawn it like a line. And if the molecular shape was linear, you might say, well, this arrow would cancel this one, but that's a trick, okay? Because in reality, is this molecule linear? Based on the VSEPR theory, I think that it's not. I think that it's not. Now, how did I know that? Because I look at my central atom and I assess the geometry around that. I've got how many groups of electron density? I've got 4. 2 bonding pairs, 2 lone pairs. That's 4 groups. In such a case, my base geometry is tetrahedral. Now, 2 of the spots in the tetrahedron have been replaced, okay, by lone pairs. So my molecular geometry here is going to be bent. I can actually have a similar geometry to water. Now, as such, I'm going to kind of draw a picture of what that molecule might look like here for our purposes today. It's really going to kind of look like this, where this is going to be my central sulfur, and then I got chlorine and chlorine, okay? That's just my color scheme I'm using for this problem. So is there any way that the bond dipole vector here and the bond dipole vector here would cancel each other out or not? There's no way they can cancel, is there? As a consequence, we've got a molecule which is polar. Slightly polar bonds, polar molecule, okay? All right, moving on to the next one. F2. This is fluorine gas, diatomic, as it exists in nature. This is the Lewis dot. We've got 2 atoms of fluorine bonded together. Is that bond polar or nonpolar? Well, if you've got the same element at each end of the bond, doesn't that make sense that you have a tug of war and both sides pull equally? You do. So in such a case, that bond's not polar. Those electrons are shared equally between these because each fluorine atom has the same tendency to pull. So the molecule has no polar bonds at all and is non-polar. Okay, move on to the next one. CS2. If I draw my Lewis dot structure for CS2, I end up with this. Around my central atom, I got a central atom that's carbon, and I've got 2 sulfurs bonded to that via 2 double bonds. So if I was to come up with a estimate of what that geometry looks like, what would I say? Well, I think it would look actually a lot like this guy, right? Carbon, we'll pretend the red is a sulfur, and this is a sulfur, okay? This is what the molecular geometry would look like. Right? Now, what I did here is I took my central carbon and evaluated how many electron groups are around it. There's 1, 2. Right? In such a case, the molecule is what? Linear molecular geometry. It's linear molecular geometry of 2 regions of electron density are surrounding the central atom, just like we see right here in this case. Okay? You with me on that? So it's a linear molecule. Now, are polar bonds present? Well, let's say, okay, maybe a little bit polar. There's not a huge difference in electronegativity between these elements, but there's going to be some difference, okay? So there might be a slight polarity here and a slight polarity here. But is the molecule as a whole polar or non-polar? I would say the molecule is not polar or non-polar. And the reason why is because this bond dipole vector or arrow would cancel out this bond dipole vector perfectly, resulting in a non-polar material. Okay. Next one is CF4. CF4. We look at the Lewis dot structures, single bonds to the central carbon. Each of the fluorine has 6 lone pair electrons to complete the octet. The central carbon has 4 bonds, completing its octet. So, what do we think about this molecule? Are these bonds polar? Definitely. Those bonds are definitely polar, because there's a huge difference in electronegativity between fluorine and carbon. Fluorine's very electronegative, carbon not so much, okay? But then the question is, well, does my molecule have a molecular dipole moment? Is it permanently polar? That's more complicated because we have to consider geometry again. So what's the base geometry if you have 4 regions of electron density around the central atom? It's tetrahedral. And in this case, there's no lone pairs, so there's 4 groups around it that form tetrahedral shape, right? So if the greens are fluorine and the black center is carbon, if I draw my 4 bond dipole vectors in, my arrows, with the negative end pointing towards the fluorine, of course, because it's the most electronegative, I think you might realize that those arrows would cancel each other out. And as a result, this molecule is not polar. It's a non-polar molecule. However, if I consider individual bonds of all these molecules, I think this bond, this carbon-fluorine bond, would be the most polar. So each bond is very polar. It's just that there's 4 of them, and they perfectly cancel each other out in space. And we have a non-polar molecule, or a molecule with no net molecular dipole moment. My last case is over here on the far right. This is similar to our second example, except now we just have 2 different atoms. We have bromine bonded to chlorine. Chlorine is slightly more electronegative, and as a result, if I was to draw my bond dipole vector, it would look something like that, okay? The positive end down here at bromine. Now, there's no way that this can cancel out with anything else because there's only 1 bond. That bond is polar, and as a result, both the bond is polar and the molecule is polar. Because there's no cancellation of the bond dipole vectors. So this molecule does have polar bonds. It does have a molecular dipole moment. This molecule, CF4, has polar bonds, but the molecule is non-polar. This molecule has slightly polar bonds, but the molecule is not polar because they cancel each other out. The bond dipole vectors cancel each other out. There's no net molecular dipole moment. This has no polar bonds, and the molecule is not polar. And this one has polar bonds, and because the molecule is bent, not linear as drawn, but it's bent, the molecule is also polar because the bond dipole vectors do not cancel.